We're going to go ahead and get started again with our next presentation from Jeff Young, who's from Georgia Institute of Technology, who will be presenting smarter NICs for faster molecular dynamics. Jeff, how are you today?
Doing good, Brian. Thank you for having me. And
absolutely.
I will say apologies to Gilad and DK. I think they probably have seen a version of this talk previously, but we wanted to bring this to the HPC AI conference, partially because we use some of the resources. So this ties in very nicely with Gilad's last question in the last session.
Perfect.
Okay, so I am Jeff Young. I'm a senior research scientist at Georgia Tech, and I work with a group called HPC Garage, which is led by Rich Fudig. And I'd like to note that this work is actually, as with most academic research, is done by a very good student, Sarah Karamati. And then we have collaborators at Sandia National Labs, Clay Hughes, Scott Himmert, Scott Levy, Whit Schoenbein, and Ryan Grant, who is now at Queen's University. So many thanks to all of them. Okay. So as we noted earlier, this slightly fuzzy picture is a Bluefield 2 smart NIC or data processing unit slash DPU. So our focus for this particular study is we want to look at smart NICs, things that have kind of a general purpose multi-core CPU. So this is a little bit different than some smart NICs that have FPGAs on them, for instance, or sort of very small computational elements. So some projects like Spin, for example, look at doing sort of small, single purpose cores, basically. But what we want to do with those Bluefields is actually a little bit different than what a lot of other users and researchers do. So specifically, we're interested in what we call off-path or separated host computation. So, what we mean by this is basically on the left-hand side, we have something that is maybe the host system. This might be like a CPU-based server. And then within that server, we also have a smart NIC, which is kind of the green box here. When we say off-path, and NVIDIA has called this many different things, I think now they refer to this as separated host mode. We actually mean that they're asynchronous and independent threads that are on both of these devices. And the NIC in this case actually runs like a small operating system. So we can, sort of do all the things that the host can do, typically just a little bit slower. We kind of contrast this with how smart NICs get used a lot of times, which is kind of a latency or deadline driven task. So in this on-path mechanism shown here, you might have like an inline task that gets performed on the smart NIC, and then it migrates some actual more extensive computation to the host CPU. So we're interested in the top model here, whereas most of the previous work has kind of looked at the on-path model. You did hear a little bit about this previously, so I won't spend a ton of time on it. Things like mVAPage DPU, and this is from the paper that describes a lot of the fundamental algorithms for mVAPage DPU. Focus on things like communication offload, kind of sort of small additional acceleration for traditional HPC applications. But we also note that there are previous studies by people like Brody Williams at Los Alamos National Lab, and they've looked at many apps and basically have said, okay, if I just map this application to my smart NIC, how well does it run? And the answer is not very well. Part of that is because there's a communication penalty between the host and the smart NIC. So if you just map an MPI application across, say, a smart NIC and a host, you won't necessarily see a benefit. Our approach here is that you actually have to look at the algorithm and do aggressive restructuring of that. Also, we note that there are a lot of emerging standards that probably change our approach here. Today, we're looking at basically multi-program MPI. So that means just an MPI program that runs on the host and on the smart NIC. But there are standards like OpenSnappy that will probably actually improve the performance of communication between a host and a SmartNIC node. Okay. So our application is MiniMD, which some of you might be familiar with as a molecular dynamics proxy app for the LAMPS larger application. And here we're showing just kind of a simplified version of this where we have 4 MPI processes, and each of these has some set of particles that it basically owns. In the distributed memory setting, each of the processes has some amount of memory. It's typically associated with one or more cores on a CPU, and the simulation proceeds in parallel on each of those processes and then exchanges data at some point. The other thing you might notice here is that there's kind of this white boundary region. This is typically where we might do our halo exchange between processes, and for MiniMD, that's also the case. So if we blow up one of these particles here, then we see there are a couple different parameters that are important for MiniMD. One of these is a cutoff distance. This basically says if I have a particle, how many other particles within my simulation are actually interacting with that and are generating force that moves the particle from one location to another. This cutoff distance specifies how many particles are actually neighbors of a particular particle, and MiniMD keeps track of all those neighbors within a neighbor list. As you might expect, there's kind of a trade-off in terms of accuracy versus speed. So, if the neighbor list is very, very large, then, when you have to do these updates, that might be computationally intensive. But there's also a trade-off that, if you don't make it big enough, you lose some accuracy with your simulation. So one of the ways that they kind of get around trying not to make the cutoff distance too large is they kind of have a buffer of some extra particles that they keep track of in addition to the neighbor list. This is the delta parameter or the skin that's specified here. So in this example here, we're kind of going back and we're saying, okay, we're in that halo region, our cutoff distance and our skin actually reaches into that halo region. So in this particular case, if we have our neighbor list for a particle, we're actually going to have to exchange data between process 1 and process 2. And we can do this at a certain rate, which is specified by the user when you run the application. So this value k, which is kind of our update parameter, specifies how often you'll actually go and do exchanges with your neighbors. Again, this is sort of a trade-off in terms of how fast is your simulation versus how accurate it is. Okay. So if we look at the baseline MiniMD algorithm, you might notice that, okay, it looks kind of complicated. We don't necessarily need to worry about all of that. But for each of these processes, you also notice that it's sort of an iterative process. There's one step that follows each other. So these run in parallel on different processes, on MPI processes, but within a process, it runs serially. There are several tasks. There are things like, sort of initializing the state. Then you're moving processors, moving atoms between processors if they move across that boundary region. Then you're building your new neighbor list based on the particles that have moved, and then you're doing some kind of communication. And then finally, at the end of each iteration, you're doing your force computation, which says, okay, for each particle, how far has it moved and how fast is it moving in each iteration? The key thing to take away here is that these are all serial dependencies. So if we want to parallelize this further on something like a blue field on a host, where previously we haven't seen a lot of speed up, if we just map the application to the blue field, we need to break those serial dependencies. To look at a more simplified version of this, we have a simulation that has a certain number of iterations. Then within those iterations, we're doing some kind of computational work. So the force computation. And then we also have this neighbor list generation and communication step. So what we want to focus on is, what do we do with this neighbor list generation? If you look at the frequency of how often this happens based on this K parameter, you might say, well, let's just move that to the blue field. And so here we see a situation where we have kind of a breakdown, maybe not quite that, but we have processor A has some of the force computation, and then processor B has a mix of neighbor build operations and force computation. And this is where we get to sort of the interesting part. On the left-hand side here, we have our serial algorithm. On the right-hand side, we have kind of the restructured algorithm. So this is all the hard work that Sarah did to sort of break this serial compute and communication algorithm down into two pieces. What you might notice here is that we did split things up. So we have the force compute, but we've put that on the blue field. And then we have the neighbor build on the host CPU. Part of that is because the neighbor build is actually a pretty computationally intensive task. So the blue field has a little bit slower CPU. It's not as well vectorized. It doesn't have as good of a cache. So it actually makes more sense to ask it to help out with the computation. And that's kind of one of our insights here is that, yes, you can split your algorithm. Obviously, there are some changes that we made to kind of, do a little bit of work on each of the host and the SmartNIC, but it may not be exactly the way that you think it should map. So you have to kind of try different iterations and in a sense, hand tune this application. Okay. So look at a little bit of the results, and this is kind of why we're here. The Thor cluster is one of the HPC AI clusters. I think there's another one, Tesla, that also has some blue fields. But this was a great platform to test on. So we use 16 nodes. Each of those has a dual socket Broadwell CPU. So that has 32 cores total. And then each of the nodes also has a ConnectX-6 adapter and a Bluefield 2 DPU, dual port SmartNIC, basically. One thing you'll note here is that, this is an 8-core ARM V8 CPU. The frequency, the megahertz is similar to the Broadwell. The performance is not quite the same. Also, there's a lot more memory on the host than there is on the Bluefield. So if you're running an application where you have kind of a very large memory requirement, right now the Bluefield 2 wouldn't be a great fit for that. So this is kind of our key takeaway, and then we'll break it down into a few more steps. But one of the things that we notice is that you can get some speed up if you sort of restructure your algorithm and map it between the host and the Bluefield. These 4 charts on the right-hand side here show the case from basically 2 hosts on the Thor cluster up to 16 hosts. These tests, I believe, are there's 1 MPI process on the host, and then there's 1 MPI process on the DPU or the SmartNIC. And the lines, the green, orange, blue, and pink lines are basically that K value or reneighboring interval. So as you might expect, as you sort of decrease the interval, as you go from every 10 time steps down to 1 time steps, that becomes a lot more overhead for the host to process. So when we add the Bluefield and we say, okay, please help out with some of the forced computation, we actually see a small but significant speed up of about 20%. So this is a pretty nice result considering, other than sort of repartitioning the code, we didn't do a lot to the code. We didn't do additional vectorization for the ARM CPU, which probably would provide a better performance benefit. We didn't, vectorize the host code. So we really just kind of restructured the code and some of the algorithms. The other key thing that we note here is that, we got a 20% speed up in sort of the kind of worst case, most frequent reneighboring situation. But, based on some data that we got from David Cho, which, he was very helpful in pulling data for us. We estimated that the Bluefield DPU used about 6% more power than kind of the host, without the DPU. So this kind of trade-off, potentially indicates that if you already have a SmartNIC in your system, we noticed that Thor has both ConnectX-6 and the DPU. If you just had the DPU, for instance, then you could potentially use this to get kind of a small performance benefit at a very reasonable power cost. And I'll just note here at the bottom, I don't have this slide in this presentation, but there's a paper version of this that will be presented at IPDPS by Sarah. And in that, we kind of go into, basically confirming that for MiniMD, this, algorithm restructuring did not affect the accuracy. Okay, so we looked at a kind of a very basic MPI case where we just sort of restructure the algorithm and split it across the blue field and the host. Then we did some more experiments. We extended that to test hybrid MPI and OpenMP algorithm. One thing you might note here is that you have the teal line that is basically just running on the Thor host. So that's saying I just have 16 MPI processes, and I have up to 2 OpenMP threads, for all the cores within a node. So if you use a small number of OpenMP threads and a large number of MPI processes, then the host will always probably be a little bit faster. But then again, you're talking about something that is substantially more power hungry than a SmartNIC. What's more interesting, we think, is that if you look at the kind of 1 to 8 thread lines here, you see that there's a performance benefit up to a certain number of threads, and then there's kind of a plateauing. And what we found is that basically after you add a certain number of OpenMP threads, there are actually some synchronization points within the algorithm that cause it to kind of not necessarily deadlock, but basically there's some contention that reduces the overall performance of the algorithm. So, the degree of overlap that you have is basically depends on, how powerful your host is and how powerful your blue field is. The other key thing to note here is these arrows kind of point to sort of the matching point for the host only and the host plus the blue field. And you notice in each case, we're getting, some recognizable benefits from adding the blue field OpenMP and MPI algorithm to the mix. All right. So very briefly talk about kind of where we want to go from these initial results we have, which we thought were pretty good, basically because those are the first kind of off-path algorithm results that we're aware of that show sort of a good benefit of running this application on the DPU. So what Sarah did is she built a performance model that takes, some of the kind of breakdown of the algorithm that we had previously and puts that into a formula that then you can kind of tweak the times for the blue field, running each of the particular pieces of the algorithm and on the host and sort of see, if you had a certain number of host cores, if you had a certain number of blue field cores and, different numbers of MPI ranks, how would your performance vary? So what you'll see here on the right is that if you look at the lower right, you'll notice that looks very much like our last graph. It is pretty much the same thing for the solid lines, but you'll also notice that these dotted lines are the predicted times by the model. So we built this model, kind of validated it with some different tests using the Thor cluster. And then, our focus there is that, say, if we wanted to look at, say, 64 nodes, or if we wanted to look at, slightly more powerful host cores or more powerful SmartNIC cores, then we can plug them into this performance model and get some reasonable estimates. So one of the final things we did in this work and this paper is that we took that performance model and then we said, okay, what if I took a Broadwell core, maybe a Broadwell-like CPU core, and I put kind of a small version of that on the SmartNIC instead of the ARM core. Or, let's say if I put a much more powerful ARM core, like a V9 SVE type CPU. Again, we kind of see this sort of plateau effect where because of that synchronization overhead within the OpenMP algorithm, it is plateauing at some point in terms of performance. But, at the same time, we are seeing about a 2.5x improvement as you sort of increase the number of OpenMP threads. And we know that you could probably do better than this. The reason that we didn't is we were more focused on kind of the splitting of the algorithm rather than the redesigning of the OpenMP version of the algorithm. So there's a lot of overhead here that we haven't really touched yet. But our takeaway from this is that if you were to use this off-path algorithm for MiniMD on kind of a higher efficiency, CPU type core on a blue field, then, it would probably do about as well as a blue field with 8 cores today. So, that's one potential takeaway is that you could do a more powerful, CPU with fewer cores on your SmartNIC and get similar performance. The other kind of takeaway here is that, this off-path algorithm also helps improve the performance of the host system. So that's another key result that we found. So in conclusion, this is obviously sort of the first step in what we hope is kind of a long journey of investigating SmartNICs as a type of off-path computational accelerator. That's not to minimize the contributions of a lot of this other work, the stuff like OpenSnappy and MVAPIS DPU. Those are all very important. But the question we're trying to look at is basically, if I'm putting a SmartNIC in my system anyway, can I get any additional accelerator benefits? And we noted here that we got about 20x speedups or 20% speedups for MiniMD at a very low power cost. And obviously that was, with some decent algorithmic restructuring, but, we didn't hit all the optimization points that we could have. One of the other things I note here is that if we look at this picture, it looks very much like what we have seen with, a CPU host and a GPU. And there, a lot of the work that was done over the past, 5 to 10 years was looking at how do we minimize communication overhead and maximize our overlap to minimize, the effects of PCI Express. We see kind of the same sort of corollary here between the SmartNIC and the host. Of course, it will require a lot of additional exploration to figure out. Okay. So I would like to say we do have a paper version. Obviously, Sarah will present the best version of this talk at IPDPS. She's still working on that. So if you would like to learn more about that, please reach out to me. I'm happy to help. Some of the things we're looking at next are kind of, communication overlapping approaches for stencils, looking at a few other applications that seem to have this breakdown. But we're very interested in this field of SmartNICs and very interested to collaborate if anybody has ideas or suggestions they'd like to work on. Finally, thanks very much to the HPC AI Council. Thanks to NVIDIA, who actually donated 2 Bluefield 2s, and we've got those installed so we can do some additional testing there. And thank you to all our collaborators.
Thank you, Jeff. Appreciate the presentation. Mm-hmm. Very happy to work with you on this. Glad our team in the Cluster Center was great in their assistance. So kudos to them. So thank you.